Given that the value of an infinite series is the limit of its partial sums, we're now going to investigate some properties of infinite series. Our first property says that if we have a convergent series, in other words, the infinite sum exists, and we multiply each term in that series by some real number, then the new series also converges. So let's take a look at why this might be the case. So let's assume we've got some series of a sub n's, and we know that that is equal to a. If we take now the new series we get by multiplying each of our terms by c, properties of addition, the distributive property tells us that we can actually factor c out of that sum. So this is going to be equal to c times the sum from n equals 0 to infinity of a sub n. But we started off under the assumption that that sum was equal to a. So this is just equal to c times a. And we now have a convincing argument that our new series also converges. A similar argument is going to show us that if we have a divergent series and multiply all of the terms in it by a constant, the new series will also diverge, assuming the constant isn't 0. So we're now assuming that the sum from n equals 0 to infinity of a sub n doesn't diverge, or does not converge. Let's look at the sum from n equals 0 to infinity of c sub a sub n, c times a sub n. We know that c times the sum from n equals 0 to infinity of a sub n, but since this diverges, in other words, this sum is infinite, c times that must also be infinite, and thus, again, a fairly straightforward argument tells us that the new series diverges as well. Our next proposition says that if we have two convergent series and we add those together, then the new series we create is also convergent. Let's look at why this might be the case. So let's assume that our sum from n equals 0 to infinity of a sub n, those add up to a, and the sum from n equals 0 to infinity of b sub n adds up to b. If we create the new sequence, the sum from n equals 0 to infinity of a sub n plus or minus b sub n, we know by the properties of sums that that has to be the sum from n equals 0 to infinity of a sub n plus or minus the sum from n equals 0 to infinity of b sub n. Because multiplication or addition splits up that way, we're using just basic properties of arithmetic here, but we already said that this was equal to a and this was equal to b, so it follows very easily that our new sum is a plus b. This next one's a little bit harder to show. Here we're trying to show that if we have one divergent sequence or series and one convergent series, that when we add or subtract them, the new sequence or series that we create also diverges. So we're going to start off by assuming that the sum from n equals 0 to infinity of our a sub n's diverges, while also assuming that the sum from n equals 0 to infinity of b sub n converges, so we'll call that limit b. We're going to use something called proof by contradiction. In proof by contradiction, what happens is you assume the opposite of what you're trying to prove, and you then get a contradiction in the process. So what we're trying to prove here is that the sum from n equals 0 to infinity of a sub n plus or minus b sub n diverges. So since we're doing this by contradiction, our initial assumption is going to be that that sum converges. So we're going to assume instead that the sum from n equals 0 to infinity of a sub n plus or minus b sub n is equal to some value, we'll call it c, which means it converges. It converges. We know that when we add or subtract two convergent sequences, we get a convergent sequence. We just showed that. So that must mean then that the sum from n equals 0 to infinity of a sub n plus or minus b sub n minus the sum from n equals 0 to infinity of the b sub n's, that has to converge, and in particular, it has to be equal to c minus b, because by our assumption, this is c, and by our initial hypothesis, this was b. So we get c minus b here. But we also know the sum from n equals 0 to infinity of a sub n plus or minus b sub n minus the sum from n equals 0 to infinity of b sub n is the same as, using just properties of addition, this is a sub n plus or minus b sub n minus b sub n. Well, these two are 0, so this is the sum from n equals 0 to infinity of a sub n. And that means that that has to be equal to c minus b. But remember, this thing diverges. So we've reached a contradiction. When that happens, that tells us that our initial assumption is false, and that the sum from n equals 0 to infinity of a sub n plus or minus b sub n must diverge, because our assumption was that it converged. That led us to a contradiction, so our assumption must be faulty. All right, our next property, our final property, tells us essentially that if we change the starting value of a sequence, it does not change, or a series, excuse me, that it does not change whether or not this series converges or diverges. So let's look at the sum from k equals 1 to infinity of a sub k. And let's start off by assuming that this converges. So in other words, let's let that sum equal some value. We'll call it a. Well, we know we can split that up. We can write that as the sum from k equals 1 to m minus 1, where m is just some given value, it's less than infinity, of a sub k, plus the sum from k equals m to infinity of a sub k. So we just broke off. This is a finite sum that we broke off. And every finite sum, because it's a finite sum, this has a value. Let's call this c. So now what we know is that a, this guy here, is the same as that, has to equal c plus the sum from k equals m to infinity of a sub k. And so what does that tell us? Well, that tells us that the sum from k equals m to infinity of a sub k must be a minus c, so it converges. I'm not going to work through the divergent case because that argument is very, very similar.